Okay. Oh, sorry. I'm all paranoid today. All right, so we left off with the projectile problem from yesterday. I didn't hand it out yet. You don't need it, just yesterday's notes. I had us start part A, where it said find the maximum height of the projectile. So to just kind of sum up what we had already done yesterday, we had taken the equation they gave us. We simplified it down to that by reducing our numerator, or our leading coefficient. All right, and then we said x is going into this function as the horizontal distance that your projectile is away from the cliff. So we're letting the y-axis act as the cliff, and then the x-axis is its horizontal distance away from that cliff. And then the y coming out was your height. And we said the projectile was launched from an original height of 500 feet, and then what goes up has to come down. And then we saw yesterday when you found the max height, first we had to find its x-coordinate, which was its horizontal distance from the cliff, and that ended up being 2,500. Then we plugged 2,500 in, and we found out that the maximum height that the rocket reached was 1,750 feet. That's what we did yesterday. Is everybody okay with that? Yes? Okay. Then it says, how far from the base of the cliff will the projectile strike the water? So guys, picture your cliff, you got water down here. The rocket's gonna go up, and then eventually it has to come down and hit right there. So that's where it's gonna hit the water. So what height is your rocket going to be at when it strikes the water right there? 0. So basically, you're trying to find out in part B, when is the height of your rocket equal to 0? Right? When is your height, your function, h of x, equal to 0? So we're trying to find x, the horizontal distance away from the cliff when your rocket will be at a height of 0, right there. Now guys, correct me if I'm wrong. If we looked at the full parabola, right, like behind the cliff technically, would it strike the water again over here? Would it have a height of 0 here as well? Yeah, so you are going to get 2 answers, but this x value is going to be what? Negative. And would it start at a negative? No. So that's the one we're going to have to get rid of. We're only going to keep the good x value, the positive x value. All right, so let's set our function equal to 0 and solve. So there's a couple things you could do here. Right away, I look at this, I'm like, oh, it's saying pretty. So normally when something's not pretty, it means it's probably not going to factor, and then you always have what method as a way to solve a quadratic equation that doesn't factor. How could you solve a quadratic equation that doesn't factor? The quadratic formula. So that's what I'm looking at. So it's not going to be the prettiest numbers, but guys, we can make it work. Now, if the fraction is going to really throw you for a loop, guys, what's the denominator of the fraction? 5,000. You could times all of your numerators by 5,000, and you would get that fraction to go away. You'd have some pretty big numbers to work with, but that's fine. At least it wouldn't be a fraction. So if that's something that would make you feel better about what numbers you have to plug into the quadratic formula, have at it. I'm going to plug in just like this. I'm going to use -1 over 5,000 as A. I'm going to use 1 as B, and I'm going to use 500 as C. So let's do it. So x will equal, the quadratic formula says this. All right, so first we have to plug in the opposite of B. Who's the opposite of B? -1, thank you so much, Julie. -1 plus or minus the square root of, now you need B squared. Guys, we can do that really easily. Who's B? And what is B squared then? What's 1 squared? I just put 1 in. And then -4, now you have to times it by A, which is not the nicest number, but we can make it work. And then times C, which is who? 500. And then that is all going to be over 2 times that not nice A value again. Now, to me, the important part about using the quadratic formula is that you don't want to round anything until maybe the end. You want to keep everything as exact as possible. So let's do this. When we go to clean this up, we're going to say -1 plus or minus the square root of 1 But let's figure out what the b squared, the minus 4ac is. So everybody plug that into your calculator, just the way I wrote it. I would literally put -4 parenthesis, -1 divided by 5,000 times 500 and hit enter. See what you get. I would try to keep it exact as possible. Actually works out to be something kind of nice. What'd you get? 0.4. So really, it's positive 0.4. So now we have 1 and a positive 0.4. So plus 0.4. Pretty nice. All right, all over. Now on this, think of it as 2 over 1. So you multiply your tops and you multiply your bottoms. So you get -2 over 5,000. If you want to reduce that, have at it. If you want to put -1 over 2,500, great. It's not necessary. It's really not. So I'm just going to say this. Okay. So right now, I feel like if I leave it like this, I can still get my answer without having to round anything until the end. So right now, we're going to get 2 answers. One answer is going to be when we take -1 and we add it with the square root, right? We're going to do the adding one of the square root of 1.4 all over -2 divided by 5,000. So guys, type this into your calculator. The numerator, but put it in parentheses, -1 plus the square root of 1.4, close catapult, divided by your denominator, put it in parentheses, and hit enter. And it'll do the entire thing for you, and you will not have to round until this part right now. And tell me what you got as x. It should be negative, if I remember correctly. What'd you get? 0. Perfect. -458.04.
So that reminder, if you are a senior that was scheduled for the acupuncture test, please check into your first period class for attendance and then report directly to the arena. Testing begins at 7:15. If you were scheduled for the acupuncture test, the test begins at 7:15 in the arena.
So that number is this x value right here. It's the one behind the cliff, when it's on the ground behind the cliff. So we get rid of it. So now your second answer should come from when you take -1 and you subtract the square root of 1.4. And then you divide it by -2 over 5,000. So we're going to type this exact same thing in again, except this time put a minus sign. All right? So we're going to plug in -1 minus the square root of 1.4 in parentheses. Keep your numerator all together. Divided by -2 divided by 5,000 and hit enter. And this should be the good one. Did you get it, Andres?
Yeah.
What'd you get?
5458.04.
5458.04. Perfect. So it will strike the ground. I'm sorry, the rocket will strike the water right there when it is 5,458-ish feet away from the base of the cliff. Okay? Now, I want everybody to practice on the graphing calculator. I want you to type this function in, and I want you to ask your calculator to calculate the 0. Have your calculator calculate that x-intercept, and make sure you can use the graphing calculator. So I'm going to do it up here. First, you got to go plug your function in. When I plug it in, I do -1 divided by 5,000 in parentheses, that leading coefficient. Like I said, fractions, I always have a tendency to put them in parentheses. X squared plus x and plus 500. And hit enter. Now, if you go to graph, again, that window, normally mine's always set from -10 to 10. Guys, we already know that this rocket, he doesn't even touch the ground until 5,458 feet. So definitely we're going to need our X's to at least go from 0 to that number. I even go past it, maybe 6,000, 7,000. Your Y's, we know that it doesn't reach its max until 1,750. So you're at least going to need your Y's to go to 0 to 1,750. So let's adjust our window so we get a better picture of this. All right, so in my window, I'm going to go, like I said, the x-axis is going to be pretty big. I always like to go backwards. I'm going to do negative 1,000, probably not necessary. And then what do we say? 5,000, so at least 6,000, maybe even 7,000, just to have a little bit of a cushion on that right side. That's some pretty big numbers. I'm going to count by at least 100, 200, 400, 500. Let's make it big. Let's count by a lot so our axis doesn't look crazy. I'm going to count by 500. All right, the Y's, we said, we got to get to at least 1,750. I'm going to at least 2,000. So I'm going to go negative, let's say 500. Because again, I like to have a little bit of a below. And then, let's say 2,500. I always, like I said, leave that cushion. Maybe I'll count by 300, 200. Let's see what that's pretty nice. Okay. All right, so now all I need you guys to do is go to that second trace button, that list of calculations, and I want you to calculate the 0. We don't need this one. We know he's the bad guy. But calculate that 0. Do the left side and right back. And make sure you can do it on your calculator. So again, the graphing calculator only has the capability of making an extremely educated estimate, right? Well, our x-axis guy, our x value, he's on point. It's 5,458.04, just like we said. If you look at the y, it's like, whoa, what is that? Guys, this is 1 times 10 to the negative 10. So that means you would have to move his decimal place 10 spaces to the left. So it's like 0.0000. So it's extremely close to a y value of 0. Sometimes that freaks students out. They're like, what is that? It's just scientific notation. It won't say exactly 0 because, again, it can only make that estimation, but it's 0. Y is 0. Okay? All right. On your homework, I'm pretty sure they put one more step to this problem, and it says something along the lines of how high it will. I think it says something along the lines of when will the height of the rocket be, or how far from the base of the cliff will the rocket be when it's at a height of, let's just say, 1,650. So then it's going to be when y is 1,600, it kind of cuts it again, and there should be 2 x values that it's at 1,600. I would just write whatever number they want it to be equal to as that y2, y equals the 1,600. Let it be that horizontal line, and then use that intersect button on your calculator to intersect the two graphs. Okay? I think they had one more step on the homework. All right, let's go to the next problem, the bridge problem. All right. This one says, the Golden Gate Bridge, a suspension bridge, spans the entrance to San Francisco Bay. Its 746-foot tall towers are 4,200 feet apart. The bridge is suspended from 2 huge cables, more than 3 feet in diameter. The 90-foot wide roadway is 220 feet above the water. The cables are parabolic in shape and touch the road at the surface at the center of the bridge. Find the height of the cable above the road at a distance of 1,000 feet from the center. It is like, what? There are so many numbers in there. Let's try and make this make sense. So let's try to draw a picture. So guys, we got the San Francisco Bay, and we have a suspension bridge, right? There's a bridge that's over the water. The bridge, it says, it has two 746-foot tall towers. And those 746-foot tall towers are 4,200 feet apart. That's what we know right now. We got two towers. They're 4,200 feet apart. The bridge is suspended from two huge cables. That's what's holding the bridge above the water, that are more than 3 feet in diameter. And the roadway that is 90 foot wide is 220 feet above the water. So guys, 220 feet above the water, there's your roadway. Now, the fact that it's 90 feet wide doesn't seem to be an issue for me. I don't think we're going to need that piece of information. The cables are parabolic in shape, and they touch the road surface at the center of the bridge. Here is, let's say, the center of the bridge. Your cables are parabolic in shape, and they touch the roadway at the surface. Okay, so again, if you can kind of picture your suspension bridge now. Your cables that would then be attached to that cable and whatnot. Okay, guys, let's call this 0, 0. It's the center of the bridge, right? So we're going to say the road itself, the bridge, is our x-axis, and we're going to let this point be our y-axis. Okay, so that is 0, 0 right there. So there's some points on this parabola that we know. We know that these two towers are 4,200 feet apart. So guys, if this is the middle, this one would be how many, feet to the right? 2,100, half of 4,200, right? And this one would be negative though, right? It's to the left? Okay. Perfect. Oh, I'm sorry. I'm labeling it wrong. This is 2,100, so that's the x coordinate, right? That's 2,100, sorry. And that's negative 2,100. My bad. All right, now, the height right here. We know this point right here has an x coordinate of 2,100. What is his y coordinate? Well, guys, the tower itself was 746 feet, but we're letting the x-axis be like ground zero. So that's 220 feet that you have to take off of his height. So from here to here, the tower is only how tall if you take off the 220 feet? 526. So that point right there is positive 2,100 as your x and 526 as the y. And the same thing over here. This point right here is left 2,100 feet, so that's negative 2,100, and it is 526 feet above the water. Okay, so we have enough information now where we could write our own quadratic equation. They didn't give us a quadratic equation to model this bridge, but we have enough where we can write our own. The easiest formula to use when you are writing the equation of a quadratic, from a graph especially, is vertex form. Y equals A times the quantity x minus h squared plus k. We already know who's our vertex. What point did we say was going to be our vertex? 0, 0. So that's h and that's k. Let's plug them in. The vertex was 0, 0. So if I clean that up, I'm going to get y equals a times, guys, what's x minus 0? X squared is? X squared times a is? Ax squared, and then plus 0, we don't got to write. So right now, that's what our quadratic equation is looking like. I need a, though. I need a value for a. I have some points that I know have to be on this graph. I know that that is a point on our parabola. So I'm going to borrow that as an x and a y to plug in, and then I'll be able to solve for my a, my leading coefficient. So I know 526 is equal to a times 2,100 squared. I'm not even going to do 2100 squared. I'm going to leave it. And then to get a by itself, all I have to do is divide it over. And then 526 divided by 2100 squared is a. So plug that right in and you've written a quadratic function. Except, let's do this. X is going to be what? The distance it is from the center of the bridge. And then Y is going to be the height of that cable. So let's call it h of x. And there is our quadratic equation. Okay, so at the end of the day, what did the question ask you to find? It said, find the height of the cable above the road. So here's your cable, and then here's your road. So the height above the road is exactly where it lands on that parabola. Find the height of the cable above the road at a distance 1,000 feet from the center. Guys, here's your center. They want to know when you are 1,000 feet from that center, what is the height of that cable? So I just need the y coordinate when x is who? 1,000. So what are you going to do with 1,000? Plug it in. Plug it in for x right there and find out what is going to be the height of that cable when x is 1,000 feet away from the center. And again, just because I have major, I would probably do this. I'd probably throw an extra set of parentheses around that. Probably not necessary, but I'm very OCD with fractions. Bless you. Anybody want, it's in the hundreds. Anybody want to say what they got as their answers or answer? I'm in the low 100s. What do you got? 119.27, and we are in feet. 119.27. Is everybody okay? Were you able to get that on your calculator? Yes? Okay. All right. So if you have another one like this, you have a picture now to go off of. To me, just imagining that is the hardest part. But now that you have a picture, everything else kind of just falls into place with different numbers. All right? All right. Let's try to get one more done off of here. I don't think we'll get both done. You guys, welcome to that's great. Y'all welcome. Nikki, okay? We did this problem, we just did this problem. So you missed it. Yes. I gave him, I walked him back one so you didn't have to. Oh, no, I gave him one. Today I gave him one. All right, I think what I'm going to shoot to do is number 2. He's the harder of the two. So let's try and get that one out of the way. Your picture is pretty dark, so hopefully you can still see. All right, look at this one. It says, a track and field playing area is in the shape of a rectangle with semicircles at each end. The inside perimeter of the track is to be 1,500 meters. What should the dimensions of the rectangle be so that the area of the rectangle is a maximum? All right, let's organize ourselves. First of all, what have they asked us to do? At the end of the day, we're trying to find what should the dimensions of the rectangle be. So I don't know how good your picture is, but we have a track that they said is a rectangle with the shape of semicircles at its end. So typical, everybody can kind of picture that as a track. All right? They want to know what the dimensions of the rectangle should be, the length and the width, so that it maximizes the area of the rectangle. So goal number 1 is we have to maximize area of the rectangle. Okay. Well, guys, if you wanted to maximize the area of your rectangle, what formula would you use to find the area of your rectangle? Area equals length times width. Okay. So it's kind of like, all right, well, if I'm going to build that function so that I can find its max, right? I'm going to have to know the dimensions of the rectangle. And right now, I do not know its length and I do not know its width. So you're kind of stuck right there, which is going to bring us to goal number 2. Goal number 2 is we're going to need a relationship between L and W so that I can write the area either all in terms of the length or I can write the area all in terms of the width. We don't want the formula that we're trying to maximize to have more than one variable living inside of it. So we need a relationship between L and W. Yes?
Are we going to go into parameters?
We're going to have to use the perimeter.
So E equals 1500.
Yeah.
And 2L times 2W. No, 2L plus 2W equals P, which is 1500.
Okay.
Equals 1500.
But the perimeter, you have to understand, the perimeter of our track, the 1500 isn't just the perimeter of the rectangle.
It says inside. So
Yeah, but I think what they mean is the perimeter of the inside track. Like if you were running around the inside, like not this one, the inside track, the perimeter of it is 1500. So the problem is the perimeter is not just the perimeter of the rectangle. And that's what we're going to have to get into in a second. So our second goal, but you're on the right track, all right, is we need a relationship between L and W. So we're going to have to look at the other information that they have given us to build that relationship. Guys, what's the only other thing they've told us about this track other than that we're trying to maximize its area? The other piece of information was the 1500, which is your perimeter. Okay, so we're going to use the perimeter and them telling us that it has to equal 1500 to build this relationship. All right, well, first of all, how would you even find the perimeter of this track? Guys, clearly, you'd have to use this right here, and that is the what of the rectangle? The length, right? I'm going to say length. Okay. So do you agree that the perimeter of our track definitely uses a length and another what? Length. Okay. Then the perimeter, all I'm missing is this semicircle, right? Which is, guys, what's the distance around a circle called? The what? The circumference, right? From side to side is your diameter, but the distance around the circle, right? Like if you were to walk around the outside, is your circumference. So isn't this like half of a circumference right here? And then this side, you're using another what? Another half of a circumference. So at the end of the day, the perimeter is going to be equal to how many L's added together? 2L. Plus, if you have half a circumference plus half a circumference, you're actually using a what circumference? One whole circumference. One circumference. Got it. Let's start filling in some other gaps. So the perimeter, which they said is who? How big is the perimeter? So put 1500 in for P equals the 2 length, which is good because we're trying to build a relationship between L and W. So we kind of want this to have L's and W's in it so I can solve it for one of the variables and know who is L equal to or who is W equal to. All right, guys, what is one circumference? Circumference is equal to 2 pi r. Hold the phone. When we're talking about this rectangle, right? We need the length, which we've labeled. We also would need his what? Width, which is also the what of your circle. Julie, yes. So your width and your diameter are the same. So guys, instead of saying 2 pi r, what's 2 times the radius equal to? Width or diameter, right? 2 times the radius is your diameter. So let's say the circumference is equal to pi times diameter. Instead of 2 pi r, let's just say it's pi times diameter. And if that's the case, then the diameter can come out, and who can go in as an equal to the diameter? The width. We did it. 2L plus pi W. So now, what you need to do is you either have to solve this for L, so you can plug it in over here and then it will all live with W's, or solve it for W and then W will be equal to something with L in it, and then this will be all in terms of L. It really doesn't matter which one. And they didn't specifically say write the area as a function of W's. Now you know you have to get W's in. It might in the homework, I don't remember exactly, but it doesn't really matter which one you solve it for unless it tells you. But I will say this. If you solve it for L, who are you eventually going to have to divide away? 2, not bad. If you solve it for W, who are you going to have to divide away? I don't like it. I'm going to solve for L, just for pure simplicity, because it looks like it would be easier to solve for L with nicer numbers. So let's do that. All right, if we solve for L, let's minus this guy over. All right, I'm just minusing my pi W to the other side. Go ahead. Oh. Did you write the first problem down? No. Okay. What's the only thing you have left to do? Divide by 2. So now, just to make this a little bit cleaner, I'm going to do 1,500 divided by 2 is 750. Minus my W's who we're kind of going after. I'm just going to say it's pi over 2 times W. Same thing. Equals L. Woo! That was a workout. So now we know who L is equal to. So now we can come over here, take L out, and plug this in, and then this will all be in terms of just W. So the area will equal 750 minus pi over 2W times W. And now let's distribute, and you'll see your quadratic function be born. Okay, so technically the way we've written this area, we have written the area as a function of what variable lives inside of it. So we've written the area as a function of the width. So we could actually call it this. Oh, you know what? My OCD. I'm going to put that first. Okay. So now, when the width of your rectangle goes in, the area of that rectangle comes out. They want us to know what dimensions should the rectangle be to maximize its area. Well, guys, look. W goes in, area comes out. That leading coefficient is negative. So would this parabola open up or down? So who's going to be his maximum point? His vertex. So we want to find the dimensions, right? They didn't ask for the max area. They asked for the dimensions. So do I want the x coordinate, which represents his width, or do I want the y coordinate of my vertex, which represents area? We're looking for the dimensions. We want the width. So all we have to do is find the x coordinate of that vertex. And what's our formula? Negative b over 2a. Let's do it. So the opposite of b is negative 750 over 2 times negative pi over 2 is a. This actually cleans up pretty nice. Guys, what happens to a 2 here and a 2 there? They cancel. So you're left with negative 750 over negative pi. What's a negative over a negative? Positive. So really our width right now in its most exact form is 750 divided by pi. The most exact width that we have is 750 divided by pi. So we know that's who our width is going to be. Now we need the other dimension, the length. And guys, we have a formula right here that says who the length is going to be equal to. So let's plug W in right there, the 750 over pi, and let's see who L is going to be. Okay, so I'm going to plug in my 750 over pi. Something nice happens. What happens to a pi on top and a pi on bottom? They cancel. I'm left with the length equaling 750 minus what's 750 divided by 2? 375. And now what's 750 minus 375? 375. So the most exact dimensions of this rectangle for us to maximize its area is when the length is equal to 375, we are in meters. And then when the width is 750 divided by pi meters. Now do me a favor, just in case the book makes us, now that we found all of our exact answers, now ask your calculator, what is 750 divided by pi? Give me 2 decimal places, get an estimated answer for your width. Oh, you got it?
No.
Go ahead.
What happened to the 750 that was over top?
When you had this, when these ones right here, yes?
Yeah.
So now you have 750 divided by 2. So 750 divided by that 2 became 375. Does that make sense?
Yeah.
Okay. Was it 2 something? 238, did you say? Point? Perfect. And you're done. Okay? All right, I'm going to stop there. Again, maybe I'm wrong. Could this be the hardest section we've done so far? Maybe. It takes time, but a lot of times the way we get to our answer is the same. It's a vertex question, or you're setting it equal to 0 and solve it, or you're setting it equal to a number they gave you and solve it. A lot of this can be done on the graphing calculator. Just watch out if they ever use the word exact. If they ever use the word exact, that's usually something that has to be calculated by hand, okay? All right. As far as homework goes, I think the track problem is the only problem that we've covered that was on my day 2. So I can do this. You tell me. Obviously, you have the day 1 homework, right? I haven't gone over any of the other problems on day 2 other than the track. I can literally just assign you the track problem for day 2. And then let you guys work on that so you weren't stressed while we went over it, try it on your own, and then that's it. Day 2 would be that problem. Maybe I'd throw one more revenue at you. And then you'd have day 1 and day 2 for the weekend. And then that's one less problem you have to worry about seeing on the day 2 homework with the other problems that I have to assign. How do we feel about that? Just the one, just with time, like ease into that one? Okay, so maybe I'll do that. I'll only assign 1, 2 problems over the weekend on top of the day 1, because I know these problems take time. But they are definitely some graphing calculator things can be done to help you, all right? All right, let's do that. I'll post that right now.